You have like abnormally large hands.
Well, yeah. I mean, I have like gorilla hands, but I mean, I'm a bigger human being than you. You know, I know I seem petite, but in real life, I'm quite large. I'm 6'5", 370. That's a bear. I just described a bear, is what I did.
What you're saying is you shouldn't travel into the North Woods
Right.
at this time of year?
Right. Hunting accidents,
Yeah.
just all over the place. So, I mean, I can use it, but, you know, I still have to stretch to get to some of the top of the screen and stuff like that. So I would say, even for me, it's a little bit of a stretch using it one hand. I'm kind of have to learn. But for most people, if you're going to get the 6 Plus, I think you're getting it with the understanding you're probably going to use it with two hands. You know, it's that device that lives between your tablet and your phone. The 6, my wife has, you know, she's really petite, and that's fine. It's not that much bigger in your hand than the 5S was, or any of the previous ones. But this one's definitely, doesn't feel like a phone anymore. It feels like a undersized tablet. All right, so DPI dots per inch. Huh? Well, I also have fat people pockets.
They make those bigger.
I can fit an iPad mini in my pocket. I can almost fit an iPad Air in my pocket. Depends on the pants.
Those cargo pants. Why would you need to put an iPad Air in your pocket?
You wouldn't have to. The point is, I could.
It's just a replacement for.
Conversation starter.
Right. It's like,
Look what I have
In my pockets.
that's my laptop. All right, so DPI, dots per inch. Is 500 DPI better than 400 DPI? Yes, no?
Not necessarily.
Not necessarily. Why?
Needs a resolution to support that DPI. Because if you have a small resolution, then your screen would be that big and it really does you no good.
Okay. So more DPI doesn't necessarily mean it's better. You know, anything over 300 we can consider to be this idea of a retina display or whatever, something that is as good of a quality as our eyes are able to detect. So we might be able to make the argument that 300 DPI is in general better than 200 DPI, but even at that, we can probably find some resolutions where it wouldn't be appropriate. So there's a kind of a marrying between the DPI, the screen resolution, and also the physical dimensions of the device that all kind of go together and produce what is considered to be a usable screen size. You know, I think when we talked about this last time, we were using the 6 and the 6 Plus as an example. Both of these phones have the same quality screen, but one of them has a smaller physical dimensions and smaller resolution, the 6, and it has 326 DPI, whereas the 6 Plus has 401 DPI. That doesn't mean the 6 Plus has the better screen. It certainly has the bigger screen, and we hope it has more DPI to support that bigger screen so we don't have all this distortion. But more DPI isn't necessarily better. Make sense? Okay. So for your homework, you were to write a second constructor, right? One that took in the horizontal resolution, the vertical resolution, the horizontal dimensions, and the vertical dimensions. Correct? Now, something that was mentioned at the end of class, I was going to have you write a second additional constructor, one that took in DPI, vertical dimensions, and horizontal dimensions. And State Farm pointed out that we would actually have a non-polymorphism problem where you'd have two constructors with the same name that literally took identical number and type of parameters. Java does not care if the variable names are different. So we couldn't have two constructors that took in 3 doubles. Now, to confront this, and we'll talk about this in a second, we will write that third one. Let me ask you this. When we're dealing with horizontal and vertical dimensions, the physical dimensions of the device, does that need to be a double? I mean, is every single phone that ever comes out something clean like 2 inches by 3 inches? Or is it typically, there's some sort of physical dimension in the middle, right? It's 2.18 by 3.46. That would be a very common thing, right? For there to be, not be clean inches. What about resolutions? Can horizontal and vertical resolutions be described as integers?
Yeah.
Have you ever heard of a resolution like 1231.68 by 1440 by 22? I just made it up. Okay, resolutions are always given as whole integers. So if we're going to update this a little bit, so let me quickly solve the homework the way that kind of you were expected to do it. So we're going to write a second constructor here. Public screen info, and this guy is going to take in a double hrez, a double vrez, a double hdim, and a double vdim. Let me minimize this. More shows up on the screen. Okay, and we're going to set all these values. But one of the values we need to get out of this is our DPI. So we need to solve for DPI. So the first thing I'm going to do is I'm going to go ahead and set all of our local variables. So this dot hrez is equal to hrez. This dot vrez is equal to vrez. This dot hdim is equal to hdim. This dot vdim is equal to vdim. Okay, now we need to go ahead and we need to solve for DPI. Okay, and if we look at our, what did we say DPI is? DPI is hrez divided by hdim, or it's vrez divided by vdim. Either one of those are acceptable measurements for DPI, right? So we're going to go ahead and say this dot DPI is equal to hrez divided by hdim. That'll be reasonable enough. So this dot DPI is equal to hrez divided by vdim. And that can actually take from these local variables. And then we can calculate screen size.
Should be HDIM.
Oh, thank you. And then we'll calculate screen size in the same way we did before. So now we have two distinct ways of creating screen info. One where we give it the DPI, the horizontal resolution, and the vertical resolution. And the other one where we can give it the horizontal vertical resolution and the horizontal and vertical dimensions. Test this out. Instead of giving it the 515, actually, before I do that, let me get our numbers here. Physical screen size is 3.73 by 2.49. Just make a second call here. Call this guy SI2. This is 3.73, 2.49. Make sure I have these in the right order. This guy's expecting resolutions followed by dimensions. So now, if I build SI2 using our new constructor, then I tell SI2 to display itself, we should get, oh, hold on, I must have put these in backwards. 2.49, 3.73. There we go. So we get a number that's pretty close because we give them rounded dimensions. So that's 514 DPI, and here's the resolution. And then the screen size for our diagonal is 4.48 in that example. Okay, so that would have been the solution to the homework assignment, is this guy right here. Now, realistically, horizontal resolution and vertical resolution, they do not need to be stored as doubles. Typically, a resolution might be 1920 by 1080, for example. That's a whole number, so we can store those as ints. Which then allows us to read in horizontal resolution as an int and vertical resolution as an int and set everything else appropriately. Similarly, in our original, we could have horizontal resolution being read in as an int, vertical resolution being read in as an int. Now we can create a second version of this constructor. I'll just steal this whole thing. That is a constructor that takes in the DPI and then takes in horizontal dimensions as a double. And vertical dimensions as a double. So even though both of these constructors take in 3 parameters, the first one takes in a double and 2 ints. The second one takes in a double, and a double. Okay, so we'll read in our HDIM, VDIM. Then we need to solve for HRES and VRES. So HRES is DPI times HDIM. And VRES is DPI times VDIM. Okay, now this is telling us that this might give us a value that isn't rounded, right? It's going to give us a double value, but I'm trying to store that inside of an integer. So if you are multiplying DPI by horizontal dimensions like 2.78, what's more appropriate, to truncate or to round? Or could you make an argument either way? Any way you cut it, we're basically estimating, correct? You know, when you go from physical dimensions to a set resolution given a DPI, you really are making kind of a rounded guess. Like we did the math last time about the Galaxy Note 4, where all the numbers we were putting in said that this guy doesn't have 500 DPI, it actually had 515 DPI, right? So they were almost giving fuzzy specs, which is actually interesting to me. It'll be, anybody getting that device when it comes out? The Galaxy Note 4? I think it's supposed to be out like in a month or something like that. I'm interested in knowing when it finally comes out what the official specs on it are. Because you would think if you're Samsung and you're trying to sell a bunch of devices, you would, if you could say 515, you would. Even though, since we're educated in here, we know that that doesn't necessarily mean better than 500. But to the average consumer, when they see Apple bragging about 401 DPI, why would they say 401? Why not just say 400? Because 401 is bigger than 400, right? Yeah. So for the average consumer, when we see the bigger numbers, we're impressed by those, correct? So when they brag about the 4K display on the Galaxy Note 4, well, first of all, 4K, well, sounds cool, right? It's the 4K OLED, super high resolution display with 2560 by 1440 or something like that. Any way you cut it, it's like all the numbers are bigger. That means better, right? So from a consumer's perspective, why wouldn't they say 515? Kind of interesting. I'm interested to know what it comes out to in the end. So we'll go ahead and we'll just typecast this to an int. We'll say, go ahead and do that math and whatever it ends up being, truncate it. Just cut the decimal place off. And we'll just take the final result. Okay, so for those of you who are currently in 250, we know that integers don't know how to hold decimal places. So if I were to take the number 3.14 and truncate it, I'd have a 3. If I took the number 3.99 and I truncated it, I had the number 3. No rounding takes place. All right, so now let's test our final version of this. So we want to put in, we're passing in, here, so we'll create an SI3. And we'll pass in DPI, we'll pass in 2.49, and we'll pass in 3.73. And then we'll call that SI3. And then we'll tell SI3 to display itself. Row. Oh, that's actually interesting. All right, so let's go through that constructor. We're passing in 515, 2.49, and 3.73. That's this guy right here. So we get our DPI. What do we solve for next? Horizontal dimensions. Well, what should horizontal dimension be? What was passed in, right? We're solving for it with a value we don't even have set yet. So this should actually just be HDIM. And this should just be VDIM. So, interesting error we ran into because we copied and pasted our code from up here. So the 3 pieces of given information we have are the 3 parameters that were passed in. The other 3 pieces of information we need to solve for. So we get 515, we get our 1920 by 1282, so we see a little rounding issue there. Not rounding, but because these numbers were given to non-exact standards, we actually rounded our 3.73 and our 2.49. These values were a little bit off. The 1920 ended up coming out okay, but the 1282 should have just been 1280. And we get our screen size of 4.48. But we see the math is working. Correct? All right, so that's kind of our DPI thing, how modern day hardware works from a screen perspective. You know, you take it one step further, there's different screen technologies, right? So, you know, all the phones prior to the Galaxy Note 4 use an LED display. Then the Galaxy Note 4 has announced this new OLED display. It's a newer take on it. So if you were to read the some of the reviews in the last week, the iPhone 6 Plus got the top rating out of all LED displays. But I doubt very much it's going to hold up from a quality of display perspective to the OLED. Just new technology. The OLED is the first screen to take advantage of this new technology. And it's not just a 4K thing. I'm sure you could have a 4K LED screen. But I don't know very much about OLED, so that's why I'm not going too much into it. But it is a newer technology that I'm sure has many advantages. And most of the things I've read about indicate that we should expect when the benchmarks come out, when they compare the 2 screens, that Samsung Galaxy Note should probably have the top screen around until 2 weeks later somebody else comes out with an OLED 4K screen. But it's that type of thing. Okay, so questions on any of this? Okay, so we learned about DPI and then we just did some applied stuff to kind of see it in action. So let's get back into this. There was our quiz. All right, so we were talking about hexadecimal representation. Decided binary was error prone for people. We don't like 1s and 0s. Binary is also not easily recognizable by people. Base 16 is more readable by humans, especially for large numbers, because we can fit it in smaller pieces. And then we talked about binary to hex conversion the long way. right? So when if I were to, I gave you a quiz, right? We did, I think that was last class or 2 classes ago, whatever it was, where you had to take a binary number and convert it into a hexadecimal number, correct? What did you do first? You took the binary number and you converted it to decimal. Then you took the decimal number and you converted it to hexadecimal. So you did it as a 2-step process, correct? All right. So what we can do, and if you remember back a couple of slides here, we talked about the bits, the nibbles, the bytes, the words, and the double words. So we're going to be dealing with nibbles quite a bit here in the next couple of classes. So when we look for a shortcut way of converting binary to hex, so we have this binary number here. We can break that number up into nibbles. So we have the last 4, 0, 1, 1. There's 1 nibble. Then we have 0, 0, 1, 0. So nibble, 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 nibble. And then finally, we have a 2-bit number in the front, which is just 1, 0. Okay? We can just go ahead and concatenate 2 zeros onto the front of that and leave us with 0, 0, 1, 0. Does that change the value of it? Is the binary number 10 any different than the binary number 0010? Same number, same number. All we did is we made this into a nibble, okay, a 4-bit number, half byte. All right, so now as we walk through this little chart here, the binary number 0 is the decimal number 0. It's also the hexadecimal number 0. The binary number 1 is also the hexadecimal number 1. Button. This is, don't think of this as an individual binary number. Think of this as a nibble. Okay? So if we're looking at the nibble 0000, that's the hex value 0. The nibble 1, hex value 1. Nibble 2, hex value 2. So on and so forth, all the way up to a 7. Now we come over here. Remember, this is the 1's place, the 2's place, the 4's place, the 8's place. So 1000 is the decimal 8. It's also the hexadecimal value 8. 1001 is a 9, then a 9. 1010 is a 10 in decimal, is an A in hex. Making sense? So, to do a conversion between binary and hexadecimal directly, what we can do is we can take the number, we can subdivide it into nibbles, like this. And then for each of the nibbles, we mark the value. So this is the hexadecimal number, hexadecimal digit 2. This is the hexadecimal digit 5. This is the hexadecimal digit E, 1110. This is the hexadecimal digit D, hexadecimal digit 2, hexadecimal digit 7. So this number in binary is equal to 25ED27 in hexadecimal. That make sense? So we're able to do the conversion directly. That's convenient, isn't it? Especially when you think about computers, as the patriarch was telling us about memory, how we use hexadecimal for addressing memory because those numbers get really, really, really big. Doesn't it seem kind of inefficient if we have to constantly go from binary to decimal, then decimal to hexadecimal? I mean, we can assume computers can do that really, really fast relative to how we can do it, but it's still going to take a long time. It'll add up, right? So we have a more convenient way of dealing with this. So what we want to do is we want to write an algorithm that will do this for us. Convert between the binary value and its hexadecimal equivalent. All right, so what we're going to do, just to keep things somewhat clean, I'm just going to write this all inside of test here. So we're going to write a couple of methods. So we're going to write a method. Oh, well, for starters, let's read in a number. Actually, it's not even read in a number. Let's just hard code a number. So we're going to say string bin is equal to, and just for our testing purposes, let's use this number. Can I copy that? No, probably not. 1001 0111. 0, 1, 1, 0, 1. 0, 1, 1, 0, 1, 0, 0, 100. I think that's it. Okay. All right. So that's our binary number. For starters, we're going to go ahead and we're going to print out this number in nibbles. We want to subdivide it into 4-bit chunks. All right, so just to kind of get the ball rolling here, we'll create a little temporary method, static void display nibbles. This guy's going to take a string s as a parameter. And we're going to take that string and we want to display it 1 nibble at a time. Now, how do we make sure that that very first value has 4 bits in it? If I want to display it, the nibbles from left to right, which is ultimately what we did here. This is the first nibble, second, third, fourth, fifth, sixth, so on and so forth. Okay? I need to make sure that there's the appropriate number of characters in my string. How do I do that? So in our current string here, we noticed that down here at the bottom, they had to append 2 zeros under the front of this first nibble. So this is, so there's 22 characters in this string, right? Let's just prove that real quick and I'll come back. So I'll just print out the length of s, and then we'll go ahead and call that method. So test.display, and we'll pass it bin. Okay, so this is going to take in that string, and we're just going to print out the length of it, which should be 22 if I copied it correctly. Okay, there's 22, or at least copied the right number of bits. It doesn't mean I copied it correctly. So how do I make sure that my value has enough forward zeros? Go ahead.
Mod it by 4 and make sure that it's equivalent to 0.
Okay, so what's 22 mod 4? So 4 goes into 22 5 times with the remainder what? 2. How many zeros do I need to put on the front? 2 of them. Okay, so I might create an integer, int num zeros, and num zeros is going to be s dot length, number of characters, mod 4. And we'll go ahead and print that value out real quick and make sure that it's the value we think it should be. So in this case, it should be a 2. So there's our 2. All right, so if s.length is 22, 22 divided by 4 is 5 with remainder 2. And now we know that's the number of zeros we need to append onto the front of it. Make sense? So what we'll do here is we're going to say s. Well, I'm going to do it this way. We're going to say for int I is equal to 0, I is less than num zeros, I plus plus. So in this case, we'll go through 2 times. So we're going to loop through some number of times. And each time we're going to say s is equal to s, or s is equal to the string 0 concatenated with s. That'll tack a couple of extra zeros onto the front of it. And for those of you in 250, we'll be talking about concatenation on Thursday. Just know that this glues these 2 strings together. So the string 1, 2, 3 concatenated with the string 4, 5 is equal to the string 1, 2, 3, 4, 5. Okay, and again, you know, even though we use a lot of programming in here, we're not looking at this as a programming class. We're looking at programming as applying the theory we're learning from the slide set. Make sense? And ultimately what will end up happening is you'll become a much better programmer because you're constantly taking ideas and turning them into working programming algorithms. Before you know it, you'll be doing this passively because it's the best way to solve a problem. Okay? So you'll thank me later, even if you hate me for the assignments right now. All right, so we're going to go through, we're going to tack on a couple of zeros. When we get to the end, if I do a system.out.println s.length, we should see it's now 24 because we've thrown 2 zeros on there in our current example. So there's our 24. Okay, now we know we can subdivide it by chunks of 4. So let's go ahead and let's print out our nibbles. So by the time we get here, we have padded S with enough zeros. And the number of zeros might be 0 zeros, correct? So if it was already evenly divisible by 4, how many times will this loop run? Let me get rid of this print statement right here. Let's say I is 0. Is 0 less than 0? It's not. And since for loops are pre-check loops, this loop will not execute even once. Okay? So we're guaranteed when we get down here that whether S has been changed or not, S has a number of digits that is evenly divisible by 4. Okay? So we've put zeros on the front if necessary. So now we want to divide this up into fourths. So for starters, we want to just go ahead and print out our nibbles. I'm going to print out the nibbles. So I want to take the first 4 bits, print them out. Then the next 4 bits, print them out. Then the next 4 bits, print them out. How would you go through S and print out 4 bits at a time?
So if you write a loop that walks through the string, and then if you print the char at, let's say we just use kind of a similar loop like that, a for loop, walk through. You say the char at index 0, which would be I, at +1, +2, +3, so those 4 chars. If you make that a string, print that, then you increment I. You might have to do times 4 instead of plus maybe.
Well,
or plus
add 4 to I.
But yeah.
First time through, we want to print out 0, 1, 2, 3. Then we want to add 4 to it because the next time through we want to do 4, 5, 6, 7. So what we'll do is we'll do a for loop. For int I is equal to 0, I is less than s dot length, I plus equals 4. So we'll add 4 to I each time. That's the same thing as saying I is equal to I plus 4. All right. And then each time through, we'll go ahead and we'll print out system.out.println empty string concatenated with s dot char at I concatenated with s dot char at I plus 1 concatenated with s dot char at I plus 2 concatenated with s dot char at I plus 3. So we'll just hard code in our 4 digits. We know that we won't walk off the end of the string because we know that our string is evenly divisible. The number of characters in our string is evenly divisible by 4. So the first time through, this will print out 0, 1, 2, 3. Next time it'll be 4, 5, 6, 7. Then 8, 9, 10, 11, so on and so forth. And then we know each time through our loop, I will become 4 greater than it was before. Okay, so instead of going through, in this case, we have 24 characters in our string, right? Instead of going through our string, let me ask you this question. How many times does this loop loop?
Length divided by 4.
Length divided by 4 times. So historically, when we've written loops to go through strings, we usually walk through each character, each individual character of the string. In this particular case, we are jumping by 4s. So we're going to walk through this string in this particular case 6 times, right? So when I run this, we should see 6 nibbles printed on the screen. 0010, 0101, 1110, 1101, 0010, 0111. Make sense? Now, these are our nibbles, and we need to turn these into the equivalent hexadecimal bits. Or hexadecimal digits is the correct way of saying it. How am I going to do that? Now we want to start turning our mind towards efficiency, because we're trying to think about how computers work. And even though we can certainly convert each of these numbers back into decimal and whatever, is that the right way to do this? Do I want to take this binary number and convert it into decimal? And then do the mapping? Or is there a better way of doing this? What are my options? Could I take 0010 and convert that into the hexadecimal digit 2? And then say, since it isn't greater than or equal to 10, we're good as is? Similarly, if I took, see, 1s, 2s, 4s, 8s. So this is the number 13 right here, right? Which is actually the hexadecimal digit what? A is 10, B is 11, C is 12, D is 13. So that's the hexadecimal digit D. So ultimately, when I go through this, I want to get the value 2, then 5, then this is the 1s, 2s, 4s, 8s, so that's 12, 14, so that's E, D, 2, 6, and that's what it should print out. Oh, this is 1s, 2s, 4s, that's 7. 4 plus 2 plus 1. All right, so we should get that value displayed. But how do we go from our binary nibble to the equivalent hexadecimal value? We have 2 options. We can do a conversion like we've done up to this point, or could we actually just do a mapping? Just say, if it's 0, 0, 0, 0, then it's a 1, or it's a 0. If it's a 0, 0, 0, 1, then it's a 1. If it's a 0, 0, 1, 0, then it's a 2, so on and so forth. Is that more efficient, doing a lookup like that? What do you think? If we were the people building a computer, and we'd have the equivalent of a computer program, a hardware circuit that we build to do this stuff, how do you think it would work? So if we think about this in terms of a hardware circuit, if we had something that is going to convert from a nibble to its hexadecimal equivalent, and I have 4 wires, all right? And the first time through, out of those 4 wires, we have a value of 0, a value of 0, a value of 1, and a value of 0, which is going to be in terms of electricity firing on those wires. So only one of those wires is live. How do I take that kind of data, those four outputs, and turn it into the hexadecimal value 1? Or I guess in this case, it's hexadecimal value 2, I'm sorry. So how do I take 4 outputs? So we draw the picture here. So I have a 0, a 0, a 1, and a 0. Okay, and we're going to think of these as our outputs. All right, so those are the values that are firing across each of these wires. So this is an electrical current, and forget how we might sample that or read from it. Let's just apply kind of our pseudo programming logic to this. So we have these 4 values, and somehow we need to get a final value of 2. This is the hexadecimal digit 2. How do I calculate that given these 4 values? What are some options? Remember, we're MacGyver. I've thrown you into a garage, and this is what you have to work with here. Just start throwing some ideas out. I'm not asking you to tell me based on your deep knowledge of computers. Just, if you were the one inventing this, what are some ways we can approach this? Yeah.
Couldn't we do what we did with that other program, making decimals go to hex, or like multiplying it times the place?
Well, possibly, but this is what you're looking at right here. I got some cables laying on the floor, and one of them's sparking. Okay? The other 3 is nothing. All right, and I somehow need to figure out how to turn 3 non-sparking cables and 1 sparking cable in a certain order. Turn that into this value. Let's go ahead and create our hexadecimal, a list of hexadecimal values. And of course, it's going to fit perfectly. No. Work. I was just being super slow. We're just going to watch this. This is a half a frame a minute. Let's do 30 by, we'll just go ahead and type it, 30. I love how it spaced so perfectly. This is a 0, this is a 1, that's a 2, that's a 3, 4, 5, 6, 7, 9, A, B. All right, so those are our hexadecimal possible hexadecimal outputs. And I'm always going to have a 4-bit input. So if we think of this like a computer method, a computer programming method, we have a method that has 4 parameters, 4 inputs. And each of those inputs is going to come in, and we're going to somehow do some logic here in the middle that will map those 4 inputs to one of these 16 values. Right? Okay, so there's 16 unique combinations here. How could we do that mapping? So I have that sitting in front of you. Now we switched over to almost a Lego problem. What are some things you might try to do?
Could you like figure out the value for each square to like convert to hexadecimal, you know, the 0 power, the first power, like 2, 4, 8, 16 plus, figure out the value for each set of 4, and once you find that value, then you can
We only have one set of 4. These are our only inputs. So what you want to do is you want to figure out what the decimal value of this is.
right, yeah.
Okay, so in that case, what we need to have is we'd have to put something here in the middle where our logic goes, something that converts between binary and decimal, right? And then for the decimal numbers greater than or equal to 10, we'd have to put another converter that maps from that to a letter. Would that work? Certainly, right? We could write the program that would do that. So we could write the program to do that with the right kind of wires and chips and stuff. We could probably write the converter. Is that the best way of doing it? Is there some sort of filter we could put here in the middle that if we hook these 4 wires into it, the filter would probably be sufficiently complex that it would fire out one of these 16 values on the other side? We know that our output from these 4 is going to be one of these 16 guys. That's factual. So think of this like a LCD screen. And whatever we type in, we have a little 4-digit code, so whatever buttons we push, we have 4 little buttons, power on, power off. We're back to the vacuum tube days, but will allow us to have buttons instead of the tubes. Okay, so we can turn them on and off. And depending on what we do here, only one of these 16 light bulbs comes on, telling us what that digit was. So in this particular case, since our input was a 0 here, a 0 here, a 1 here, and a 0 here, we know that we should have the 2 light up. How did we figure that out? Well, one way we can do it is we can convert the math. We can do the math of this, right? How do we know this is a 2? We know this guy's worth a power of 1. This guy's worth a power of 2. This guy's worth a power of 4. This guy's worth a power of 8. So this guy counts once, this guy counts 2 times, this guy counts 4 times, this guy counts 8 times. Right? So if we put some piece of equipment here in the middle, just call it a mult for right now. Keeping it simple. Okay. And this particular chip, wiring stuff, you think of what's a computer chip? A computer chip is something we can do by hand with a bunch of wires and soldering, cleaned up to look nice. All right, so usually when we deal with computer engineering, dealing with hardware, somebody designs the circuit in this really, well, nowadays they're designing it in computer screens with digital software and stuff like that. But in the old days, somebody would have sat there in the early Apple computer days when Wozniak was building the first Apple I. He would have sat there with wires and crap and a battery powering this stuff, hooking all this stuff up. So even the simplest problem would just look like a pile of wires laying there. But in the end, the correct little light showed up, letting you know that things were working. All right? And then once you had the problem solved correctly, then they went into, VLSI, very large scale integration, where they took all this complicated stuff and they turned it into a little tiny black square that had all the same guts organized in really little tiny wires, so that it would actually do the same job in a much smaller footprint. That makes sense? So that's how we get from crazy ugly computers the size of gymnasiums to laptops and even smaller devices. Right? Although today we're not dealing with vacuum tubes and stuff. We actually have a battery. We can hook it into a digital board and all this other stuff. So we're going to call these multipliers for right now. We know that this guy is going to take this value and multiply it by 1. We know that this guy is going to take this value and multiply it by 2. This guy is going to take this value and multiply it by 4. This guy is going to take this value and multiply it by 8. And then we're going to get a little output out of that, giving us a new digit. Correct? So let me shorten these up a little bit. All right, so these guys are going to ultimately have something like this. Fire out of them. And then we will shorten those up too. And just so we can keep this compact. How long were those? Those were 420. Okay, we can't have it like that because it's based on the distance. All right, so now our value coming out of this is going to be what? This will be 0 times 8, which is 0. This will be 0 times 4, which is a 0. This will be a 1 times 2, which is a 2. This will be a 0 times a 1, which is a 0. Something like this. We have a problem. How do we represent a 2? Two is something human beings like. Computers, we have to use digital logic. We represent a 2 as, with a 2-bit number, 1 on switch, 1 off switch. Electricity. It's a binary number. So we actually went backwards. We calculated 2, that if we want to store that 2, we have to do what with it? Turn it back into binary. But we can still do the multiplication. But now we got to talk about how we're going to represent that output. So for right now, we can leave it as this 2. We're just representing that 2 somehow. What are we going to do with it? So now I have this. I have 0, 0, 2, 0. We want to add all those numbers together, correct? Adding all those together gives us an ultimate final answer. In this case, it'll be 2, telling us that this particular input, for this nibble of input, is equal to an output of 2. Okay? So let's assume that I have an output of 2. How do I map it over to my list of hexadecimal digits? So that only the number 2 lights up. We think about all those as light bulbs. And if we provide power to any one of those, it lights up. So we're starting to think in terms of how do we solve these kinds of problems in hardware. Now we could create a whole bunch of wires and attach 16 wires to each of these. And we can say, if this guy's a 0, and this guy's a 0, and this guy's a 1, and this guy's a 0, if all those things are true, using a bunch of ands and or gates. So that would be, well, I don't even want to talk too much about that in detail right now, but we have little helper functions, helper chips when we deal with hardware called gates. And a gate lets us have 2 inputs and gives us 1 output. So an AND gate would require both inputs to be on, a 1, to give us an output of a 1. Or if even one of the inputs is a 0, no electricity, then the output would be a 0. An OR gate would only require one of the 2 inputs to be a 1, to have power. So at least one of the inputs has power. Then you have an XOR gate, a XOR gate, and we'll talk about these in a lot more detail later on this semester. But an XOR gate requires only exactly one of the inputs to be on or off. Well, in this case, to be on. A NOR gate requires exactly one to be off. It's a not OR. So given that, we could come up with some sort of wiry looking algorithm that based on 16 wires coming out of each of these. So I mean that's a lot of wires, correct? We have 64 wires coming out of this. And each of those 64 wires are going to go into some AND and OR gates and ultimately have 1 wire going to each of these. And depending on what kind of magic flow through crap that went on in this middle, the body of our program, if you will, only one of those light bulbs lights up. So we did a mapping. Now, is that a conversion? What's different between doing that and taking the number 0010 and turning it into a 2? In this particular case, did we turn 0010 into a 2? We did. That's exactly what we did here, right? The means to an end change. When you're doing this in hardware, it's kind of like if you were writing something in a low-level language, where every little step you take is exactly one instruction on the CPU. So this little process chip that we're going to make here, this little utility, is going to be reasonably complex looking when it comes down to the pile of wires we have sitting in front of us just to have one nibble show up one of the 16 lights. Seems like such a simple problem, correct? It's kind of the power of programming languages. Really the power of high-level languages. It allows us to do this in a significantly easier way. So, if you were writing the code for this, where our job was just to accomplish the task, not really worrying about how fast it accomplished the task. Whenever you deal with hardware, you're pretty much going to, that's why they call it hardwire the solution. Electricity is going to flow and it's going to hit all these different filters and paths and stuff like that, and in the end it just fires out and there's your answer. Even though it just went on a pretty complex trip in the middle. With our programming languages, those trips are just as complex. Just our high-level language hides it from us. If we were writing that conversion tool in a low-level language, where we're loading, like an assembly language, we're loading a certain value into register AX and another value into register BX, then adding them together and putting it in register C, it would be this level of complexity. But we have our high-level languages allow us to accomplish things without having to deal with this low-level complexity. And similar things exist in the hardware world today, where you can go out and you can buy a multiplier or an adder or a half adder. These are things we're going to talk about in here. You can buy these compound chips that already exist, where you can plug 4 inputs into this guy and it gives you 1 output, and you know in the middle that there's some complex crap. But you also know that you didn't have to do that. You're just utilizing the tool and getting your result. Okay? So something we'll talk about, and you know, it's something that drives the price of hardware, if you followed it. Usually when a company's coming out with a new processor or a new graphics card, something like that, one of the things that drives the price of it is the current cost of Xor chips. XOR chips. Not AND chips and not OR chips. Sometimes if it's not XOR, it'll be NAND chips. NAND. That's not AND. Every gate can be defined in terms of XORs and NANDs. So you actually never need an AND gate or an OR gate if you're a hardware developer. So rather than them keeping all these individual gates on hand, they just buy piles and piles and piles of the universal gates at some sort of bulk pricing so they can build whatever they want. Kind of makes sense? And these are some of the things that drive the price of hardware. All right, so if we're going to go back here and we want to do our mapping, we'll do the shortcut thing here just for the sake of time. So we're going to create a string temp. Start that off as the empty string. Oh, we got to do this a little bit. Well, this is fine. Instead of printing this out, we're going to say temp is equal to this. Okay, so after this, temp is equal to the string representation of our nibble. All right, now we want to do something to that. So I can say integer dot parseInt, and we'll give it temp, and we'll give it a 2. This is the built-in way of converting the binary representation of a number in a string into a digit, into decimal, rather. So we're going to take 10, what was it, 0010. That's what temp will hold, and we're telling this is in base 2. This guy will boil down to the number 2, the decimal version of that. Okay?
Temp is holding a lot more than that.
No, it's not. This time through, temp is just holding a nibble.
Oh, right, yeah.
Yep. We're overwriting temp each time through the loop. Just holds our nibble. So this will be the value 2. What I'll do up here for our converter, I'll say string map is equal to 0. That's all of our hexadecimal digits, right? And then we'll just do system.out.println map.char at whatever this guy converted to. So if it was a 2, it'll give us a 2. If it was a 10, it'll give us an A, so on and so forth. So now when we run this, we get 25ED27. 25ED27 did our conversion for us. That makes sense? So even though we kind of rushed through this piece here, we took our nibble converted it from binary to, we can call it a decimal digit, we can call it a hexadecimal digit right here. And then we mapped it so that 10 would be an A, 11 would be B, things we've already done. Okay? But what this guy does is this little algorithm right here converts from binary to hexadecimal directly. Make sense? One nibble at a time. So it's kind of showing us that there are shortcut advantages of using those two bases in computing. Binary and hexadecimal have very quick conversion tools to go between each other. And next time we'll look at going back the other direction. We'll see it's not very difficult to convert from between hexadecimal and binary. Okay? And then we're going to look at binary coded decimals, BCDs. All right, I'll see everybody on Thursday.